I thank both the organizers and the coordinator of this session. Uh, I'm assuming that most of you are younger students, so at any point, if you don't understand something, just stop and uh, you can ask me any question at any point of time. Okay, there it is. Share. Okay. Think I can view in presentation mode. Okay, there we go. So what I'm going to describe is a certain amount of work we started doing many years ago. It's kind of a very long old story. About 2008 or 2009 we started trying to build up a QKD setup. uh, we had our ups and downs on it, and one student got a PhD not exactly building a QKD setup. We had some uh, technical and understanding issues about uh, single photon measurements. I'm kind of telling this bit because by now they would have told you a lot about the quantum cryptography. I'm sure there was a session, although I kind of did not really look for it in the sessions, but I'm sure there was at least one session where somebody explained to you what is quantum cryptography. If it's not been done, I'll very briefly tell. Please let me know if it's already been done. I'm assuming that it's been done. The quantum, the something called a BB84 protocol. Someone can tell me, some student can tell me it's been done or not. It's been discussed. Otherwise, it'll be a bit difficult for me to make you appreciate what is this. I mean, you don't need BB84 for most part of this, but is that someone, the coordinator would not know, but somebody would have.
Can you give a brief on it?
Sorry, it was not audible for me. I'm sorry.
Yeah, somebody has written that it is better to have actually brief
Okay,
than a BB. Yeah.
okay. So give me 2 minutes. So basically, um, what happens then? I'll have to write down because I didn't make the presentation. So let me just see if my writing works. Okay. So what happens in a Bernard Prasad 84 is that uh, Alice and Bob are supposed to exchange the key, not the message itself. In a quantum limit, the message gets transmitted later on in a normal this thing. So Alice and Bob exchange the key. Key will be a random number, random sequence of zeros and ones, preferably the size of the message itself. Okay, these messages are usually short and simple messages. Nobody wants to send a whole autobiography on quantum encrypted thing. So key will be as long as the message, and key will be generated at the time just before the transmission of the message. Okay, so the whole protocol involves generation of the key, and then checking whether the key is all right, kind of thing. In between, there'll be handshaking, authentication. Some of the electrical communication engineering students already are familiar with these words. Others, it makes common sense. So there is a handshaking, authentication, then the key generation, the key is exchanged, and then the key fidelity improvement, all those things, noise corrections, all are done. Then once the key is reliable, the actual message is encrypted and transmitted. Now what happens is that uh, because of the rules of quantum mechanics, I'll tell you very briefly that whenever eavesdropper intercepts and reads the message, the eavesdroppers will leave a footprint. Because quantum mechanics, it says that if whenever you try to measure, there's a little bit of an additional operative there. I'll come to that operative. whenever you try to measure, the measurement is also a part of the system. Unlike classical mechanics, in classical mechanics, suppose when we do a Newtonian mechanics, a tennis ball is rolling, and I'm going to look at the velocity position of the tennis ball at every time. My measurement process does not disturb the ball, so I'm kind of neglect what happens to the ball when I measure. I cannot do that in quantum mechanics. It has to become a part of the system. Therefore, now I'm going to ask a question: will it disturb? Will it not disturb? There are situations where it will not disturb. I'll explain that in a minute. There are situations when it disturbs. Okay. So, therefore, the disturbance leaves a footprint, and what Alice and Bob will do is how much of noise is there in their system at the end of the transmission of the key. Once the key is transmitted, they will look for take a small part of that and then compare and see how much is the percentage noise, not the whole key. Small part they'll take, openly read it out and say what is the percentage of noise. If there is any measurement by eavesdropper, uh, there will be a signature of the measurement, and therefore then there is a classical uh, communication theorem which says that it had nothing to do with cryptography. It had to do with how much of noise you can noise you can tolerate in a system. The classical, I'm talking of the classical communication scheme. And if the noise level is below a certain threshold limit, then doing an error correction code, a mathematical error correction code, would improve the improve the reliability of the information, and it'll improve the information. It'll denoise the information. Okay, at the last slide of my talk, I'm going to show you some effect of this one, a classical error correction code. How does it do it? But not how does it do it, but rather the effect of that one. On the other hand, if the noise is above a threshold, even if you do any classical error correction codes, it's not going to help you. Okay. So for example, just to give you, there is an error correction called the Hamming code, which probably the only one that I know of, because I'm not from the communication background. There are many. So in the Hamming error correction code, it says out of every 7 bits, if there is one bit flip, you can correct it. If there are more than one bit flip per every 7 bits, so that you can compute the percentage of bit flips. Uh, you cannot correct it if there are more using the Hamming error. You have to use some other error corrections code. So each error correction code has some limitations, and there is a ultimate limitation that no error correction code works if there's too much of noise. What the communication theory people have what the quantum cryptography people have turned it around is that you twist it around and say that if Eve has above threshold information, then not above threshold. So now you're not looking at noise, you're looking at information content. If Eve has information content, is minus the noise basically. So if you have 10% noise, you have 90% information. So if the Eve has more information content, then the Eve can use classical error correction codes and improve her reliable her amount of information. So they have done some calculations to theoretically. I'll not go too much into detail. Um, uh, so they have put some threshold limit telling if Bob's information is this much, and if Eve's information is also the same, then noise correction will help both of them. Basically, you don't want to help Eve. You want to help only Bob. Okay. So which essentially means that Bob should have more information than Eve. It's more of a common sense thing. If Bob's information content is more than that of Eve's information content, then any error correction codes will have. Sorry, yeah, tell me. No, I'm not doing my slides. I've just kept my slide. Okay, because see what happened is I did not make slides about the QKD, the BB84 protocol. Okay, I made about what I since somebody said maybe briefly do it. I'm just going to very first I'm going to tell you what is the whole idea behind it, and then I'll tell you what is the actual protocol. Okay, so I'm going to write something and show you a little later. Okay, so I'll have to find out how to go from uh, this to whiteboard. Just hold on for a second. This the problem of having the problem of having a online meeting is that there'll be a lot of okay, yeah, can you see some scribblings that I'm doing? Is that visible? No, okay, hold on. Okay, new share, right? I have to do new share, right? Good. I've not used much of this Zoom thing. Now you can see, right? This. Okay. So what sorry, uh here is not working. Okay, so what we will do is so Alice and now Alice, what Alice will do is, so this is the whole idea. So if whenever Eve measures, Eve leaves a footprint, and you know how much is the footprint, kind of thing. So how does Alice and Bob get the footprint? It's a very interesting way. So now what Alice does is that okay, no, hold on. Sorry, stop sharing. Share screen. I'm sorry about this. Okay, we'll go. Let me go over here and then I will come back in a minute. I kind of go a bit back and forth, so you have to excuse me on this. Right. First is what is polarization shift keying, and then in the meanwhile, I can also keep explaining to you what is this idea about the QKD, BB84 protocol. No, so this was something I had done for a communication people, so it kind of just roughly go through it. Light as carrier is better because 10 power 15 hertz. I hope there are a few engineering students around. Go look at what is this amplitude modulation and what is the bandwidth, because the carrier frequency is very high, bandwidth is much better. Physics students also can go and see what is amplitude modulation. I insist that you go and see it for yourself. Fiber is of course best for optical communication because loss in a fiber is very less. Also, it's almost impossible to tap a fiber and steal the information. I mean, for a normal electrical cable which is carrying information like your standard BNC cable, I can always put a wire loop around it without disturbing this, and I can pick up whatever the secondaries coming in. I cannot do it for optics. Can do for optics, but I have to do too much of damage to the fiber, and you will know immediately if I'm picking up something. Um, if there is no fiber laid as yet, free space optical communication is very good, because we were doing for a free space. So I'm just kind of explaining why the free space portion and all comes. And if there's a mobile vehicle, I can't have a fiber tether to it. Can have, but the free space is much better. Fibers cannot be laid from earth to satellite. So free space optical communication is has its advantages. It also has its disadvantages. I'll come to the disadvantages. The first, so this is where I want to talk. There is normally what people do in a standard fiber optic communication is light on is 1, light off is 0. So your digital bits are, if your uh, bit is um, so this is what I wanted to show. So if your data is 110100, your normal electrical pulse will be a 5 volt, what is called as a transistor logic, TTL pulse for short. And so this is 1 1 1. Then there are two empty spaces for 0, and one more 1 and two empty spaces for 0. Whereas on a fiber optic, light on, light off, light on, light on is 1. So this is 1 1 1 0 1 1 0 1 0 0. Okay, so this is what is called as, both of them are called return to 0, because it goes up and it comes down. Now there are some things which are not exactly return not exactly to 0, but return to some other lower thing, threshold. 5 volts is 1, 3 volts is 0, or some such thing you can do. You essentially you can define your own protocol for that. Then every other protocol has to set it for you. What I mean is, you can just go plug your fiber in a fiber port and expect everything to work nicely. If you are setting up just a local communication network, you can do any protocol. But if your local network has to join to the global network, then you have to make sure that protocols are same. So there are some standardization. The polarization shift keying, it does not work in a fiber, because usually fiber, when light goes, it loses its polarization information. It doesn't maintain unless you are in a PM fiber. PM fibers are expensive. PM is polarization maintaining fiber, but it works beautifully in free space. So in polarization, this thing we define at this in my protocol. I am defining. You can define it in any which way. That vertical is 1. Vertically polarized is 1. Horizontally polarized is 0. So 1 1 0 0 1 0 1. I made a mistake from this one. Uh, Bear with me on that. It was supposed to be 0 as according to this, but this is 1. Anyway, no, I think I have messed it up here. Okay, these two are not same. Doesn't matter. Uh, then I can also have a 45-degree polarization as 1, and a 135-degree uh, polarization as 0. So all basically you need to do is this and this are orthogonal to each other. Okay, why orthogonal to each other? I'll come to that one. So um, I'll talk about that in a minute. Why orthogonal? So I need so now light polarization is giving me a much more flexibility. I have, in this case, I only had a light on, light off. Of course, I can do two colored lights. I can do red light on, red light off, and green light on, green light off. That will give me a flexibility, and I can also add blue light on, blue light off. But at the other end, I have to know which one is which light I'm talking about. You can be fancy, and you can use all the RGB and send everything on a single channel. So you are basically increasing the channel capacity. Um, it's a little bit difficult here, but this also gives you flexibility of choosing what we call as a basis. So this is a basis where vertical and horizontal. So we put that together and call that as a plus basis. And this, as we call it as a cross basis, because it's 45 degrees and 135 degrees. So if I write both of them together, this will be plus basis, and this is cross basis. So what happens now in a QKD? I'll tell you this part. The polarization modulation is advantageous because here what happens is, suppose my detector does not detect this bit for some weird reason. I'm going to assume it to be zero. Maybe it was not zero at all. Whereas here there is no loss of a bit. If I don't get light pulse of vertically polarized or horizontally polarized, I know I have not got a lost bit. So I have one missing bit. It's not, I'm not going to assume it to be zero. So that wrong thing is not there. It's in free space, it's cheaper, you don't need fibers. But there are also disadvantages. The biggest disadvantage is that especially when I'm doing an atmosphere, it's going to suffer atmospheric effect as fog, smoke, and particles scatterer, etc. Not only there is a signal attenuation, but most importantly, there's a polarization scrambling. So I'm going to mostly talk about our initial work on how to overcome polarization scrambling. And although a part of it, and of course later on I'm going to go talk about the QKD simulation, etc. Although the initial experimental work was not about quantum cryptography, it was a first stage before quantum cryptography, because I'm not an engineer. I came from a physics background, and then when I started putting up a communication setup, the first thing that came is, how do I overcome noise? Okay, the biggest noise source in this case is the polarization noise. So instead of right away doing single photon pulses, and then I have no idea what is coming at the end, whether I'm really getting a signal or it's some other fancy thing, we started working on uh, large pulses with more photons in a pulse. And as we uh, mm, went through, there were some communication issues that had to be solved. And after that, my student got his degree and went away, and somehow we have not come back to the quantum cryptography yet, because I had some other projects running on at that time. And hopefully sometime later we'll come back and restart everything, and we'll see how it goes. Okay, so I'll come back to this particular thing. I'll come back to this uh, particular thing. Let me see if I had a. Uh, okay, I seem to have something on cryptography also. Uh, okay, so can I do a new share? New share, new share, new share. Okay. Didn't pick up. Just hold on for a sec. And because of all these things, my setup. Okay, so very briefly on quantum cryptography. So what this is something called Bennett Brassard 84. Uh, I'm going to same thing again. I've started with the whole thing. I was doing it, and I suddenly realized that I had a very old presentation. Um, Okay, this is where this is Charles Bennett, Gilles Brassard. The first presentation came up in Bangalore in 1984. They presented this, but after that, not many people kind of took it up immediately for various reasons, and only of late there's been a very big uh, mm, punch on it. And for the past 2 years, government of India is putting also a lot of might behind it, telling do quantum cryptography, and there are a couple of labs which have taken it up. It's quite a lot of money, not enough proposals, not enough going on the experimental side. A couple of labs in India have already taken it up seriously. but there are more options. Anyway, so let me explain what on earth is this whole thing is about. Before that, a little bit of physics. The physics is this. This is an equipment called beam. You can see this beam splitter picture, guys. Yes, this picture of beam splitter, the beam splitter quantum
Yes,
mechanics.
sir.
Yes, good. Okay, right. Now, why beam splitter is a quantum mechanical device? This is something called a cube beam splitter. Some of you would have seen it. What happens in a beam splitter, a normal beam splitter, is if I send a light, half of the light will go in the transmission mode and half of the light will come in reflection mode. Exactly 50-50. Okay. This picture represents something more than that, but I'll come to that. Now, the question is what happens if I send a single photon? Okay. Now, single photon cannot be split into two. What is the meaning of half intensity? If I send a very big large beam of light, half the intensity will go in the transmission mode, half the intensity will come in the reflection mode. 50%, 50% intensity. That means that if I send 1,000 photons, 500 photons will go here, 500 photons will go here. We don't know which photon will go over here or which photon will come here. For a normal beam splitter, don't get misled by this particular picture. This is called a polarizing beam splitter. I'll come to that also. So we don't know offhand a priori which photon will go here, which photon will come here. So this is a very nice coin toss kind of experiment. If I have a series of single photons coming through, a priori I don't know whether it will go here or here. It will either go here or here, depending on 50% probability. Okay, that is as far as a normal beam splitter is concerned. With a single photon will either get transmitted or will get reflected with a 50% probability. Now, polarizing beam splitter is a different animal. So what it does is, if I send a unpolarized beam like this, uh, then all the vertically polarized beam, which means for those of you who have forgotten what it is, polarization, the electric field is oscillating only this way. When the light is propagating in this direction, electric field will oscillate anywhere provided perpendicular to this direction. It can be vertical, horizontal, 45 degrees, 135 degrees, 60 degrees, 180 degrees, any which way. Okay, 120 degrees, any which way it can do. But when such a light comes over here, all the vertical polarized lights will come over here and all the horizontal lights will come over here. Again, now what happens with a single photon? Single photon, when it comes here, if it's vertical, it will go here. If its polarization state is horizontal, it will come here. So for a polarizing beam splitter, single photon, I know what exactly it does, provided it's vertical or horizontal. But a 45-degree polarization, this is your back to your high school vector algebra. If I have a vector written at 45 degrees, I can resolve it into x component and y component and they will be equal. Okay. If I have a vector at 45 degrees, exactly like this, I know you can write it at horizontal degrees and vertical degrees, it will be equal. And therefore, something very funny happens when a single photon at 45 degrees come incident on this particular polarizing beam splitter. That single photon will now, the polarization of that single photon will be resolved into vertical and horizontal. Okay, it has equal probability. So the 45-degree polarized photon incident on a polarizing beam splitter will come either here or here. Not only that, after it comes out, its polarization state has been changed. If it comes out here, the 45-degree polarization has been changed into vertical polarization. If it comes out here, its polarization has been changed into horizontal. So now this is what leaves the fingerprint now. So suppose I have sent a 45-degree photon, and if eavesdropper is measuring with the polarizing beam splitter kept in a vertical way, then the photon which comes out would have changed its state of polarization. It will no longer remain 45 degrees. So it's changed uh, completely. It's not like during transmission it will come back to 45 degrees. It will remain there unless I do something to it. Okay. Similarly, if I can rotate this cube slightly off, if you can see my picture, this is vertical, vertical, horizontal. If I rotate this fellow like this, now this is 45 degrees, and what comes out here is 135 degrees. Okay, so it will come here and it will come this side. Okay, and then I send a vertical photon, vertical polarized photon. What will happen? It will either become 45 degree or it will become 135 degree when it comes out with a 50-50 probability. I don't know what happens a priori. Okay, it can happen anything. Now, this is the phenomena that BBID4 protocol exploits. I can give a mathematical explanation to this, that my 45-degree polarization state itself can be written as a vertical or a horizontal polarized state, which you have done in physics, students have done in quantum mechanics. This is a superposition state, and one of them will be coming out. So this is equivalent to what in quantum mechanics they always talked of collapse of wave function. So polarizing beam splitter will collapse the wave function into one of the polarization states. It's just equivalent. It's not the same thing. It's equivalent. Keep in mind. Okay, so now what will happen is this. So Alice is here, Bob is here. This is for those of you who are a little bit of history buffs. This girl in this picture is a little girl called Alice Liddell, and uh, Lewis Carroll, whose real name was I forgot his real name. Anyway, Charles Ludwig Dodgson. Okay, that was his real name. He wrote a book called Alice in Wonderland. For those of you who have not read the book, and the way the story developed was that he had a friend who was a fellow he was actually a mathematician. He was teaching mathematics in Cambridge University, and there was a fellow mathematician, Dr. Liddell, Professor Liddell, and Alice was, there were three daughters. Alice was the youngest of that, and one day they all went on a boat, and Charles Dodgson started telling a story about a young girl called Alice, and that's what later on got developed into Alice in Wonderland. He was also an amateur photographer in the very early days, 1800s, and this is one of the picture he has taken of Alice. This is the singer Bob Marley, and this is Eva Braun, Hitler's girlfriend, and this photograph was probably taken by Hitler himself. So this was all on internet. I just stole it and put onto this one to represent Alice, Bob, and eavesdropper. Okay. So Alice has to send a message to Bob, and an eavesdropper is sitting there in the middle and doing it. So what Alice does is this. Suppose your message was 0110101010. So it's a digital message. It may mean something. Doesn't right now it doesn't matter what it means. What Alice does is she has to send one by one. She has to first transmit 0, then transmit 1, then transmit 1, then transmit 0, then transmit 1. It has to go on like that. So for each bit, she picks up, she first says, okay, it is done in polarization coding, but she fixes up vertical polarization or horizontal polarization or 45-degree polarization or 135. So if you take any two bases, pick a basis first. For each bit, you randomly pick one basis. So for example, here for the first basis, Alice picks up a cross basis. That means this will be 135-degree photon. And for one, she picks up a plus basis. So this becomes a vertical photon. If this was 0, it would have become horizontal photon. And again, for this, she picks up a cross basis because this is 1. It's a 45-degree photon. So probably, oh, I have not put those things. So this will be 135, vertical, 45, again 135, 40, vertical, horizontal, 45, horizontal, vertical, 135. That will be the polarization stage for these fellows. Okay, and she sends it. Now, Bob, who is receiving all these things, doesn't know which basis Alice is sending. So, what he does is he also says, okay, first photon comes, I'll randomly choose. It may match with, we know that it has to be either plus basis or horizontal basis. So, I'll put my polarizing beam splitter either this way, I'm doing 40 plus basis, or I'll put it this way, 45 basis. Okay, this way or this way. So, he's randomly doing this. Okay, and as and when the photon comes, he is going to pick up, and assuming that each photon does come, I have not lost the photon, is one of these two detectors will pick it up. If the detector comes here, it's 45 degrees. If the detector, if this detector clicks, it will be 135 degrees. When I'm doing this, if this detector clicks, it's vertical degree. If this detector clicks, it's horizontal polarization. So like that, he will note down which detector has clicked, D1, D2, D3, D4. Among them, he will note down which one has clicked. Okay. They don't know. Now, the lucky fact is if Alice basis and Bob's basis are matched, which is a 50% chance, you have measured in the same basis as Alice has sent, so you would have got the same information. Okay. This is equivalent in a quantum mechanical language if you have a state psi and your measurement is a Hamiltonian, for those of you who are familiar with this language, and if the psi is an eigenstate of the Hamiltonian, then psi is not disturbed. I get a measurement, I get E psi, and I get a measurement value E without disturbing H. If psi is not an eigenstate of the Hamiltonian, then operation of the Hamiltonian will lead it into time evolution. Dou psi by dou t is equal to h psi. IH cross dou psi by dou t is equal to h psi. So it will lead into a time evolution. I'm doing a classical analog of quantum system because polarization is not a, even though single photon is a quantum mechanical system, measuring a polarization is not a quantum mechanical measurement, it's a classical measurement, and I'm doing a classical measurement but mapping it to a mathematics of quantum mechanics. Okay, measurement is not quantum. The quantum happens because the single photon cannot be divided. That's why the quantum happens. Because it's a quantum mechanical particle, and also when Eve measures it in the wrong basis, she's going to collapse the wave function in a wrong basis. So that's how she leaves a footprint. Okay, so now what Alice and Bob do is Alice will tell, okay, I sent you first bit in cross basis, second bit in plus basis, third bit in cross basis. For she's not telling you what is the value of the bit, she's only telling you which basis it was sent. And Bob retains anything which where the plus and cross are matching. Anything which is not matching, he will throw it off. It's called the shifted key, and so you're pretty much lost half. If you started with 100 bits transmitted, I have ended up with 50 bits. Now what they do is they take a small portion and do a comparison. So out of 100 bits they'll take 10 and compare. Let's say I send over 200 bits, and 100 bits have to be discarded. I don't know which one will be discarded a priori. Post, I'll always know which bit to be discarded, and then I will take a small portion of it, 100 bits, and compare. Alice publicly says this is what I sent you for these 100 bits. Bob takes the same 100 bits and sees whether he measured the same thing. Because the bases were same, he is in principle supposed to have measured the same information. If Alice has sent 0, Bob is supposed to have received 0. If Alice has sent 1, Bob is supposed to have received 1 and recorded 1. But assume that there is a bit flip. Okay, now this bit flip can happen due to any reason. It can happen due to a channel noise, It can happen due to my electronics have misbehaved right at that point. Let us say fourth bit was misbehaved. It's flipped. Alice has sent 0 and I have measured 1. But what they are going to say is, I'll assume that everything is because Eve has measured something, my channel is very nice. Therefore, worst case scenario is that Eve has measured, therefore the bit has flipped. Okay, I'll come to that little bit of maths over there. Don't worry about all this quantum mechanics. I don't have time for this as of now. So this is what would happen. Alice has sent this. Bob has matching things. They'll retain. This is not matching. They'll throw it off. This is not matching. They'll throw it off. Uh, so finally, I have a shifted key. Don't worry about this maths also. I'm just going to skip all the maths. I'm going to skip all this maths. Maybe sometime later I can share this. There are some typos in this, so I won't want to share this also. Um, okay, I don't worry about all this also. Okay, so basically what has happened is this. Now, eavesdropper. So a bit is coming. Now eavesdropper will toss a coin. I don't know whether it is plus basis or cross basis. For a moment, let's assume that it's a cross basis. Luck would have it, Alice also would have sent in a cross basis. Alice has sent in a cross basis. Eve is sitting in the middle before the photon goes to Bob and measuring. Nobody knows the presence of Eve. So Eve puts her beam splitter in a cross basis. Photon comes. Now, because it's the same basis, it's like an eigenstate of the system. So the system itself not disturbed. So whatever Alice has sent in, I am getting in the same way, and I measure it and I record it. I would have a correct. I don't know whether I have got a correct one yet, because I don't know if Alice sent in a cross basis. I measured it in a cross basis. If Alice had also luckily sent in a cross basis, my information is correct. But what is the chance? It's 50-50, because I'm using only Alice has sent either in plus basis or cross basis. So it's a 50-50 chance. There's a 50-50 chance that I'm correct. And let's say I am the eavesdropper right now. Okay. Now, a very funny situation. Alice has sent in the plus basis. I have measured in the cross basis, and photon has come out this side, and I have said I don't know whether she sent it. So I have recorded it. If Alice sends it in cross basis, this would have been 0, right? This would have been 1, this would have been 0, so this is 0. So I have recorded, let us say 43rd bit, cross basis 0, but now I find that Alice has sent in the plus basis. Okay, I still don't know what is the information, but here is a funny thing. It can only be 0 or 1. Okay, Alice could have sent either 0 or 1. So even if my basis is wrong, there is a 50-50 chance that my bit recording is correct. I have recorded 43rd bit is 0. It could have as well been correct. Alice could have sent 0 in plus basis. I have measured in cross basis. I have luckily measured it as 0, and I have put it down. On the other hand, Alice could have sent 1 in the plus basis. If I also measured in plus basis, there is no way I can be wrong. But Alice has sent in plus basis 1, and I have measured in cross basis. And because in the cross basis the superposition can go either way, I have got the photon here, and I have measured it as 1. I have recorded it as 1. I have recorded it as 1 cross, but it has actually sorry, I have, yeah, Alice has sent 0 plus. Okay. So if you look at the statistics, there's very funny. 50% of time my basis is right, therefore my answer is also right. Either of the answers, this answer or this answer. And other 50% of time my basis is wrong, but the answer is right. So totally 25% of 75% of time for the eavesdropper answer is right. 25% answer is wrong. Okay, it may look funny. Where is safety in this thing? 75% answer is right, but I'll come to that. 25% answer is wrong, but in 100-bit long, when Bob and Alice make a shifted key, when they throw away all the unwanted keys, and they pick up one key and then they find that it is wrong, their immediate connection is this is all because of Eve, which means Eve has at least measured 4 bits. Because only 1 in 4 bits, she is going to cause a bit flip. Okay? Because the rest of the bit flips come nicely. So 1 in 4 bits, she has caused a bit flip. Therefore, if I get one wrong bit, Eve probably measured 4 bits, out of which she has 3 bits of correct information. This fellow is wrong. So I am able to find out what is the upper limit for Eve's information. For every wrong bit, every bit flip, it corresponds to 3 bits of information for Eve. Now, the only, again, one more nice assumption is this. If Eve measures all the bits, okay, I'll definitely know if I have a 75% bit flip rate, I'll definitely know there is an eavesdropper sitting there and measuring. Okay, I'm going to drop the protocol and start afresh. Now, Eve, it's not going to help you. It can help you in one way. This is in computer science, they call it denial of service. So I'll go on jamming your system so you cannot communicate to the other fellow. There are two things. There are two ways I can harm you if you are sending a message across. Either I'll surreptitiously come and take what message you are sending. It could be coordinates for a military operation, for example, or it could be a bank password, civilian operation. You are sharing your bank password with your friend, close friend, and I surreptitiously come and take it off. Okay, you will never know that I have taken it off. I have tapped your telephone line and taken it off. That is one way. Second way is I'll keep on telling you my presence so that you will never send the message across to the other guy. Okay, I'll see to it that you no advantage to me, but no advantage to you either. I have just simply spoiled your communication. Your friend cannot withdraw money from your bank account. Okay, this is called denial of service. I will make my presence felt so that every communication channel, oh, this fellow is listening every time, right? You can't share your secret with your friend. Denial of service. Okay, so now you of course can do denial of service, but sorry, I have only 10 minutes more, so I have not been able to tell you what all we did. So let me just finish a little more. Um, so now what Alice and Bob do is they find a statistical probability of how to, how much Eve has a bit information, right? I'm not going to the statistics. There's some kind of maths over which tells that about 17% of noise. I think this 17% is wrong. My student is telling me it's 11% noise, which could be the correct thing. 11% of noise. If there is more than 11% of noise, that means for every 100 bits Eve has measured 44 bits, and she has 33 bits of sorry, what am I, yeah, 33 bits of information she has, and 11 bits of information she has messed it up with. So I'm getting it as noise bit. And there is some math says that that is sufficient enough for a fidelity improvement using classical error correction codes. So I'm going to drop the protocol. I have not sent the message at all. Message is still safe, and I'm going to redo the whole protocol to generate a key. Remember, this is only key I'm sending. I'm trying to send across the key, and if I find that there is no eavesdropper at all, I'm going to use that key and send across the information. So if I'm kind of spending a lot of time on it because a lot of people misunderstand these issues, and you have to know this part. So if the message key has been compromised, I'm going to drop the key. I'm not going to. Yes, Prabhat, tell me. Please ask. Go ahead. I think you will. The host has to unmute. Can I unmute? I don't think I can. Um, not used to this Zoom Zoom thing. I'm more of a
Yeah,
Google Classroom. Yeah. Yes,
you
Prabhat.
no no yeah, you go ahead, you finish it, and we'll
Huh.
see actually his
Okay.
question
Sure.
later on. Yeah.
Okay. Fine. 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 So, so what we have done is we know that Eve's presence, so we know that the key has been compromised, so we don't use the key. That means message is still safe. So we keep on doing this, going round and round about till the key is safe. Till I'm convinced that the key is safe, there is no eavesdropper. Eavesdropper has not been benefited anyway because she's only getting key, which is a random number sequence. Doesn't mean anything. Message has not been transmitted. Okay, so that talks about there are some issues about it. There are some commercial quantum key cryptography experiments. This is a very old slide. This was the plug and play instrument in those days. I'm sure they've changed a lot. There is one more Bangalore company which is also, it's called Q New, and they are also have an equipment in the market which they say you can just plug and it will do whatever you are thinking it's doing. Um, so that's all about QKD assets. So I hope I've explained the QKD, and I'll tell you what we are doing in the next uh, 7 8 minutes. Just let me just go a little over 4 or 5 minutes extra, and so this is the biggest problem was that this won't work in single photon level. What I'm going to show you, I'm supposed to send single photon. Sending multiple photons doesn't work. So because of atmospheric scattering, there will be um, randomization of polarization. Can you see this picture? Static, snake, ballistic, and such photons. I have changed the sharing thing. Oh, okay. I know. I'll have to. Sorry, I'll have to do a new sharing. I should have done a new sharing. Okay, so now here this is okay. So what happens is that if I send a couple of photons, some of them do a multiple scattering. It loses polarization information because that's what I finally have. Some of them scatter a little bit. They do lose polarization, but not so much. They are called snake photons. Some photons go through right away. These are lucky ones. They are called what is it called? Ballistic photons, and they do not uh, lose any polarization information because they have not uh, got scattered. Okay. So the idea is that we will look at only ballistic. If I send several photons, I'll only look at ballistic photons. Okay. So this was an experimental setup we did. I told you two bases and two random bases and two random 0 or 1, and this is represented by 0 in vertical basis, 1 in vertical basis. There's a halfway plate here to tilt everything. So 0 in horizontal basis, 1 in 0 in one cross basis, 1 in cross basis, 1 and 0 in vertical, 1 and 0 in cross basis. Can be turned the other way around. And so based on our QKD information, what Alice decides, one of them will randomly fire, and I'll have a 1 plus or 1 1 cross, or 0 plus or 0 cross. And we had a small glass chamber in the middle, which where we could fill in fog or smoke, and on the other side we have a set of beam splitters and set of detectors which tell us whether it was a vertical photon, horizontal photon, 135 photon or 45-degree photon. And this was this was a proposed experimental setup which kind of never put it up. This was the transmitter part, this was the receiver part. We put everything, but then we didn't use it because we had some issues. The only thing I'll tell you about is that initially we said, oh, we'll not do QKD, we are only going to do a free space communication in polarization. Vertical, horizontal. Don't worry about cross basis. Vertical is 1, horizontal is 0. So therefore, at the other end, we have only two detectors. If it's vertical, D1 will give me. If it is horizontal, D2 will give me a signal. And so I'll look at the signal between D1 and D2. Right now, don't think of single photons. Think of multiple photons coming. And I'll get a finite number for D1, a finite number for D2, and then I will calculate D1 minus D2 divided by D1 plus D2. What I mean by this is this. If I send all vertical photons, all of them will go to D1. Nothing goes to D2. Therefore, D1 will be 1, D2 will be 0. I mean, when I normalize it this way. So D1 minus D2 will be 1. And let's say D1 is N. Doesn't matter. You will get the same thing. So S will be 1. Suppose I send horizontal light. N photons of horizontal light. And nothing happens to them during the atmosphere. So therefore, they all are going to reach D2, and D1 nothing will reach. So D1 minus D2 divided by D1 plus D2 will be minus 1. So if I get 1 plus 1, I know I have sent vertical photon. If I get minus 1, I know I have sent horizontal photon. The plus point is that if there was any change of polarization, I'll know here itself. It won't be plus 1 or minus 1. It will be some number in between. Okay. So yeah, that's what it was. So what we did is we simply took a statistics just to see how our things work, and we find that uh, one side, the minus 45-degree polarization, this what is it showing you is a histogram. That is how many times I got 0, how many times I got s equal to plus 1, how many times I got to s equal to minus 1. First thing you will immediately tell me is that these things are not coinciding with plus 1 and minus 1. So this is about 0.6, this is about 0.8 or 0.9. So already there is a randomization, polarization, scrambling happening quite a lot. Okay. Secondly, it also tells me that this is narrow. So although polarization scrambling is happening for this, not so much of scrambling, whereas this is a broader curve. So therefore, the polarization of this is more distributed from minus 1 all the way up to minus 0.7 or something here, minus 0.75. Whereas here it is plus point 8 to 0.7. So the spread here is less, the spread here is more. So we know that there is also a bias in the system. By looking at this itself, I am able to tell the system characteristics for you. Okay, so that is one part. So we created smoke, we created fog, and we took 10,000 almost 1 lakh random bits, and experimental data, and we got our reportage of the histogram. From the reportage of the histogram, we calculated the Q factor. The traditional Q factor is this. We kind of modified our Q factor to take horizontal and vertical, because in the traditional Q factor, 0 means no light. Okay. And what we did is that we could increase an amount of smoke. More smoke in the system, more randomization. Less smoke, less randomization. So when we increase the amount of smoke in the system, and the way we measured and recorded the amount of smoke was transmitting a probe beam through it and looking at the attenuation. Therefore you will find this funny. This is 0, minus 5 dB, minus 10 dB, minus 15 dB, minus 30 dB attenuation. Okay, so that means on this way, if you go in the reverse direction, you have more smoke. This is less smoke, this is more smoke. Okay, now the Q quality factor is interesting. As you come increase the smoke, the quality factor is neatly dropping down. Okay, this is exponentially dropping down. And which essentially, what is the meaning of quality factor dropping down? That means my information content is becoming bad and bad. Okay. Okay, but I'm not going to I'll just very briefly explain this one. Now what I have is, I have sent a light, which I sent a polarized light, and it got partially unpolarized. So I can replace this as p component of it remained polarization, 1 minus p component lost its polarization. Okay. At the polarizing beam splitter, what happens? The p component which is polarized will go only to d1. Okay, it won't go on the other side because I'm using a polarizing beam splitter. And the unpolarized component will get resolved into two components. Half of it will go to d1, half of it will go to d2. Okay, therefore when I my d1 will have pi plus half of 1 minus pi. What will d2 have? Half of 1 minus pi. So if I subtract 1 from the other, I'll be subtracting 1 minus p of I, and I'm left with only p of I. So no matter how much of um, depolarization it can happen, okay, as long as your p of I is a very static, nice this thing, and that is not changing, it will remain after this formula. Which formula I need to look at? I need to look at. I need to look at. Okay, I'm not getting back to that. I need to look at the definition of S, which was d1 minus d2 divided by d1 plus d2. When I do d1 minus d2, only p of I will remain. Only the polarization part will remain. It doesn't matter what it is. Okay, I've explained this. So don't worry about Stokes parameter. We did a whole lot of Muller matrix calculation also to show that if I do S equal to d1 minus d2 divided by d1 plus d2, whether I do Jones matrices or Muller matrices, I'll be removing all the unpolarized components. I'll be measuring only the polarized components. Small, but I'll be measuring only this. When I measure small over a nearly zero background, it's easy to find. Okay, these are all the Muller matrix calculation. These two have been published. I can give you a um, this thing later. You can look at it later. Okay. Okay, so this was all done by my PhD student who is this was an old slide. I'm sorry I've not changed it. He in fact went to Dubai, joined a company to make a quantum cryptography equipment. Uh, developed some modules, not the full QKD, but developed some modules. Then because of pandemic, etc., he had to come back, and he's in Delhi right now. He's teaching in Delhi. Okay. So the last bit, just 3 more minutes, this will be done. So recently, one of my MSc students, her name was Elin Ahmed, she wanted to do a simulation project. So what we did is wrote a Python code to simulate QKD. So I have explained you all the whole QKD. So we started how it's easy to simulate. So first is Alice has to generate two sets of random numbers, the basis random numbers and bit random numbers, because because quantum key is also a bit of random numbers. Okay, we are kind of overdone on this. We generate one set of random numbers, share them between Alice. My program shares between Alice, Bob, and Eve. We we need to share it that way, because in reality they will all be generating their own random numbers. So instead of generating the same thing four times in my computer program, I generated once and shared between them. But then Python is a pseudo random number code, so we cross check for it, and it sometimes gives absolutely rubbish with respect to the this one. So what you are seeing here is how many zeros I've got, how many ones I've got. You can easily see there's a bit of bias on this one, and but the bias is quite less. And this is a representation of how many times have I got a pair like 1 and 0, 0 0, 0 1, 1 1. So I'm looking for a predictability. If I've got 0 bit now, what will be the next fellow? And the next fellow is almost 25% to the same. So this is a good set of data, and we take this data and we do what eavesdropper would do. We can determine how many bits Alice sends and how many of them Eve measures. So it's not in sequential. Eve randomly picks up a bit and says I measure it or I don't measure it. So essentially, she's going to toss a weighted coin. If it's 50-50, she measures it or not measures it. But if it is zero point 0.9, that means zero point 0.9 times she does not measure, only zero point 0.1 times she measures. Of course, it's not correct thing. I mean, you will not get much information, but because it's only binary, can we build it up using error correction codes? Okay.
Actually, we are running a little bit late. Can you actually wind up so quickly?
Yes, so the last two slides,
Yeah,
this
sure,
and the
sure,
next one.
sure.
Okay, I'm right there. Okay, so this is the most important thing I wanted to share with all of you. So what, because this is a highlight of her work. So what she has done is, Eve decides not to measure all of them. One means she measures all of them. She could decide to measure 80% or 60%, etc. And this is Alice Eve fidelity. So how many bits Eve realistically knows after she measures, and she puts on a Hamming error correction code. So the whole idea of error correction code is this: the the symptoms of errors is shared by Alice to Bob over public channel. So Eve also has access to this. Okay. So Eve uses the same symptoms to do error correction, and this blue is before error correction. After error correction, Eve's uh, fidelity has um, actually not improved at all. It should have gone much higher. It should have gone here on this side, because she should have got a better fidelity. But you can see that she doesn't have a good fidelity at all. So this is a proof telling that error correction codes is really not helping Eve. Okay, the more she measures, the more noise she is creating. Okay, but this is an interesting thing. What is happening to Bob's information? Okay, the more Eve measures, the more noise Bob has. Okay, so as Eve measures more, Bob is also not being helped, because Bob has more noise. I cannot correct infinite amount of noise. I can only correct finite amount of noise, and you will see that that stops somewhere here. So up to here we can correct very well. Okay, this is before error correction, and what you see here is multiple events done, and curve fitting done for this. Okay, this is the average of all the multiple events, and statistically he can do an error correction, very good error correction. His information is almost close to one, as much as this much of information. If he has a little more information, he has less, but not bad. He's still error corrected, but when he comes here, his error correction goes hopeless. Error correction is doing, but not much. And beyond this threshold limit, error correction is spoiling more of Bob's data. Even he was better off without error before error correction. His error correction is making it worse. Okay, for Eve, pretty much error correction is making worse throughout. So that was a interesting result of our simulation. So I hope I have done justice and you have understood most of what I have talked. So questions now.
Yeah.
Thank you. Thank you.
Thank you, Professor Ashoka. Yeah. Now the session is open for the question. We'll take only 1 or 2 questions if there is any.
There was a hand raised. I don't know what was that.
Maybe it is by mistake the person raised. Maybe.
If nobody is asking, can I ask a question?
Sure.
Sure,
Yes.
sure.
Yeah.
See your count, for after scattering looks more like a random number statistics. Random number.
No. Oh, you mean scattered data? You're looking at the histogram, right? You're asking about
Right.
the
Counts
histogram.
versus
Yes. It is. It is coming like a random number. So if you are looking for a random number, you can do it. But I mean, it has a nice Gaussian distribution. If that's what you're. Yes. But it's centered around a point. So we look
correct.
at this. We take that center point
Yeah.
and use that as our information.
Thanks.
The S value will be that information.
Yeah.
So if what we do is, if S value is positive, we will say it was 1. If S value is negative, we will say it was 0. Okay. So we just simply map it. Round off. For that. See, this has a biggest advantage. As long as S value is non-zero, I can still map. Okay. So even if I have a lot of noise, S value is plus 0.1, I can still map it to 1. S value is minus 0.1, I can still map it to 0.
Okay. Yeah, we'll discuss about it. I have some more things to discuss about that.
We'll discuss about it.
Sure. Okay, let's wind up this session, and thanks, Professor Ashoka, once more.
Yes.
Okay, let's move actually to the third talk and the last talk of 2 days. So let us, the third speaker is actually Professor Anil